Welcome back. In this video, we're going to talk about how to find the probability of a range of sample proportions using a sampling distribution. This video is a follow-up on a previous video where we talked about how the sampling distribution is defined, so if you haven't watched that one yet, I highly recommend it because we're going to pick up right where we left off. In either case, here's a quick recap of what we covered last time. So we started out with a hypothetical scenario where we had a population of 1,500 students in a large data science course. We collected data on those individuals and found that 60% of them were Mac users and the remainder were Windows users. From that population, we drew many samples which each had their own sample proportions that were slightly different from the population proportion. We plotted the simulated results of many sample proportions on a histogram and found it to be approximately normal. And we found that the parameters used to generate the normal distribution was that the mean had to be the population proportion, which in this case was 0.6, and the standard deviation was the population proportion multiplied by its complement, divided by the sample size, and the square root of that whole thing. In this video, we want to build on those ideas and see that if we have a population proportion and a sample size, can we calculate the probability of seeing a sample proportion that's at least as extreme as some value? So let's say we know that 60% of our data science course uses Macs. What's the probability that in a sample of 100 students, at least 66% of them are Mac users? We'll start by analyzing this question from the discrete scenario. So below is the sampling distribution for 100,000 samples of size 100. I've gone ahead and highlighted all of the samples which had a sample proportion, or p-hat, of 66% or greater. How do we find the probability of pulling out one of these samples? You might be able to guess that we can just count up all of the samples in the highlighted region and divide by the total number of samples to get that probability. In this case, 11,127 samples, or 11.13% of samples, had a sample proportion of at least 66%. This also means that 11.13% of the area of the sampling distribution is represented by our highlighted region. We can use this concept to find the probability under the continuous representation. I'm going to walk through how to do this using a TI-84, although there are many ways to do this, including using integrals if you have no friends. Start by clicking second, then vars to pull up the menu of distributions. Press 2 to pull up the screen for doing a normal cumulative density function. Next, we need to insert the values that are relevant to our scenario. The lower bound, or left side of the highlighted region, is 66%. The upper bound is technically infinity, but our calculator is a little old and doesn't know how to do that, so you can put in 1e99, or if you put in 999, it'll work just fine. The mean is 60%, and for the standard deviation, I prefer to put in the whole square root, but putting in 0.0490 works fine as well. Press enter twice to paste and then compute our function, and we'll find that 11.03% of the area under the curve is represented by the highlighted region. This is really close to what we got with the discrete scenario. They're a little bit off because of the randomness involved in generating the histogram on the right, so the probability generated under the normal curve is actually more accurate. That's all for now. Once again, here's a couple of practice problems so that you can hopefully apply what you've learned. I encourage you to try them out and leave your solutions in the comment section below. In the next one, we're going to extend on these ideas and talk about confidence intervals for a population proportion.